Hello, Ernest. How you doing?
Hello.
We'll wait a few minutes for everybody to join, okay? I'm gonna check out the assignments on the notes.
Okay.
Hi, everyone. How are you? Okay. So while we wait, you can check out your unit 2 on Canvas. Hi, Josh. How are you?
Hi, Professor. I'm good. And you?
Okay. I just got off another class and office hours. So I barely came into my office right now. Yeah, but it's discrete structure time. I love teaching this class. It's always so fun.
Are
So
we going to be programming today?
this week, not today. We are going to cover the math concept today, and then on Thursday, we are going to do some C++. From here on out, we are going to do C++. So. Yeah, so check out Canvas. I posted the assignments. Sorry about the confusion with the week 1 assignment. I had duplicated things.
Yeah.
I'll fix the grade. When they copied a shell from a year ago, but I wanted something from last semester, so I recopied it and it double. I thought that it would merge, but it didn't. So I clear everything up right already. So I'll fix the grade for, so if you submit one and the other or the other, I will update all your grades. I'm still working on that. So we're gonna do logic gates today. And okay, so let's see. So check out your notes. We are going to cover chapter 2 and 3. We'll start in 1 minute. My clock says 5:59. So, and then also download the assignment or view within the page. So I'll try to upload the video for today's session right after. If I don't make it, because sometimes YouTube does require a little bit of time to convert it over. It will be available tomorrow morning. But if you subscribe, you should have a playlist, and the video on there right now is from last semester. I update it every semester, mostly for most classes. In some cases, if it's exactly the same, sometime I don't have time, then I will keep it from the prior semester. But so if you want to go back and watch it, you should be able to. I know the one from last week went up last week. Okay, so we are, oh, I think I'm on, are you able to hear me okay? My microphone says that it's, I get voice.
I can hear you.
Okay, So I think for those of you who can't hear me, just check your Zoom sound configuration. Sometime it default back to your system, and if you're using your headphone, you have to configure it. Okay, everybody okay? Any question before we start? All right, so I'm gonna share screen. If you can unmute and ask question, and if you do type it in the chat, I'll get to your questions shortly. Okay. All right, so this week we are doing unit 2. I'm sure you got a message from me. We are gonna go through logic and truth table, and we are gonna do some programming, really easy ones. This class is, the only complex things might be like the project, but we will work in small parts, and then you can see the big picture as far as the project goes. So I will post the recording for today on this page. Your notes, you need to take a look at that. It's here, or if you have read the textbook, it's very close to the textbook. And then we are going to do the assignment right now. So that will be logic and truth table. For Thursday, we are going to use C++ to look at bitwise logical operators and Boolean values. So we will work with those using C++. And I will walk you through the lab, okay? Just like how I walked you through the assignment. So it'll be easy. 1 second, let me get my assignment going. Okay, so compare last semester to this semester, you are actually on track. As far as assignment goes, last semester I spent a little bit more time on the lecture, so some of that got pushed into week 2, like the two's complement. So we took care of the two's complement last week. We did number representation last week. We did binary, hexadecimal, and octal. So in this week, we are going to touch on logic gates. This topic will also be revisited in CIS7, as CIS7 is about assembly programming, and assembly is low level. So here, as you look through the notes, this chapter 2 starts with talking about digital circuits. In computer science, you will find that there will be courses that will address digital, and also, the logic gates topic will come up in many different classes. So wanted just to give you the brief overview on logic gates. So when you're looking at the processor, whether it's Intel, AMD, or others, like if you're looking at a smartphone, your processor could come from Qualcomm or a company that produce it. Your processor is constructed with many digital circuits, which is known as your logic gates. And using the logic gates from the programming side, we're able to apply a lot of different things, especially conditions. So when you're thinking about, like, when you hear the talk about machine learning or artificial intelligence, a lot of that, the model for those are just generally applying the appropriate conditions, narrowing it down to a specific algorithm that's going to be used for an intended purposes. Like, so my algorithm can be to look at, the search pattern for the user. So I can advertise the type of products that that user normally look for. So if somebody is looking for paint, there will be marketing strategies to advertise paint to that individual. In our world, the way that we write simpler program, we would apply that with if-else statement, with loops. And so what you see is you would see these logical operators being incorporated. And at at the machine level, it would use something like your digital circuits in order to operate it, right? Because ultimately your system is constructed of digital circuits, and when your CPU, like I said, that would be logic gates. So when you're playing games on the Xbox, right, or PlayStation, or even your PC, you would find that all of these things that will be presented to you is computed, is processed, and all of this is owed to your logic gates. So over time, what we would see is that your logic gates is built into what we know as transistors. And just to give you the overall idea of what gates and transistor would look like. So a transistor can be physically looking like this, okay? So basically it's just an electronic component, and it would have these 3 prongs, okay? And these 3 prongs are designed to do source, sink, and gate. And so now they can be very small, or they can be about like maybe close to 1/2 inch. So in a CPU, in your processor, you would see billions of transistors at a very tiny physical size, okay? So that link gives you the general idea. And so now in a diagram, you often see that it would be drawn something like this: source, gate, and then sink, okay? So the analogy that they use on this website is like a faucet. So when you have something that's off, or what we know as 0, right? That means that, let's say you turn the faucet off, your source, you stop the water from flowing, that will be off here. So your gates, it's gonna close right here. When it's open, when we lift that up, the water is gonna flow through. We are gonna receive full signal, and that will be on, which is 1. So when we have off, that's 0, and then 1, that is on. So here it talks about how the transistor as the faucet. And I wanted to use this web page because it gives you like the visual, and the book does somewhat similar thing, but you can see a little bit more explanation on this. Okay, so when you build the bigger circuits, right, you might have combination of these logics. Sometimes we might have, like last week we learned about the 2's complement, and I mentioned that the ones complement is when we flip the bits or we NOT it, right? So at that point, what you're gonna have is you're gonna have a NOT circuit, or the NOT gate. And so that's gonna change the composition of your byte by converting the 1s to the 0 and the 0 to the 1s. So, or some cases we would apply other type of logic like AND, or combination of those, not AND, not OR, what we call NAND and NOR, right? So in C++, you often see the logical operator being used like AND and OR, and not like when you use an exclamation point. So some language would use a certain symbol to represent the logic, okay? So here it gives you a little bit more explanation. I encourage you to take a look at it, because in the upper division classes, they're going to revisit this. So when we're looking at the battery, right, like how you're going to have the input. So the computer always going to have some kind of input, whether we input from the actual hardware device like keyboard, mouse, touchscreen, voice recognition, or we can simply use input like from a storage data. When you're pulling storage, data from the cloud, from a certain server, from database, that's also considered an input for the computer to really analyze. So when we're looking at the system, like, making the decision and presented that decision to the user, it needed some form of input, some kind of data that's need to be pulled. So here gives you a little bit more of the visual on X and Y, right? And then how that's applied to the function using the AND operator. And so we will look at the bitwise stuff right now from the mathematical perspective. and then we will do the programming so you can have a general understanding. And so now we are going to get in depth with the logic. So if you're ever curious about how many, right, how many transistors that make up your CPU that you currently use, Wikipedia has a good page. So you can search for a number of transistor, right, in a certain Intel, let's say Intel i9. Okay. And so here Google serves us and it tells us 77 million transistors, some of them more. So Wikipedia has a table just to show you, right? So if we're looking at the earlier years, like the 70s, so this is when we start to see consumer PC being introduced, right? If you read into Apple and Microsoft history. Now, outside of your consumer PC, we would see other processors. So outside of the Intel or the AMD, you would see processors that are being used for other type of system, possibly communication systems, computational systems, even IBM based. So you have a list of all different things. So as you go down, you would look at this column and you would find that your transistor count, and this is the MOS, you would see that it's increasing, right? So the way that we design the processor, because we need more complex computation, and remember I said that your computer, your processor is a calculator, right? It calculates, it only adds. So as we use it for different things, like now we're using it for gaming, we're using it for web application and so on, we design our system to really meet to accommodate the needs of the general usage, right? Our purpose. So we can go down to some of the later system, and as you can see, it would get to the thousands and then eventually millions. Okay. So when we're looking at like the quad core i7, so right here, you're already seeing about 731 million. Okay. And then from the i7 to transition to the i9, pretty close. And so if you're into other type of processor, you can take a look, and some of these are for mobile platforms. And then, and then if you're an Xbox user, you can see here's the Xbox, right? 5 billion. And that was in 2013. So if we get closer to the current day, go down further, like 2020 is when it's logged. So if you like AMD like I do, right, you see here's the Epic, much higher. Okay, that was in 2019. The Ryzen 9, also very high. So we're looking at billions or more, right? Millions or more transistors that are built into our processor, which is very tiny, that would go onto the board, and which makes a system. And if you're using like the Apple system, here's the A12. So when you're shopping around for Apple devices, you can take a look at the processor. So now you kind of know a little bit about the composition of the processor, what that would be, and how that would, yield the output that you would see, things that you use, app that you would have. Snapdragon, the Qualcomm, that one is usually on Android. I know companies like HTC and Samsung and some other company, they would use the Qualcomm Snapdragons and so on. So and these mostly you would see that they are used, they're using ARM, which is at the assembly level. That's the language, and it uses C compiler. So when you take my assembly class, I'll explain more a lot about assembly language and how that would relate to C or C++ or other higher level programming language. Okay, so this table gives you the general idea of the transistors count, and that comes back to what we talk about today, which is logic. Any question? Okay, so we said that the transistor is a digital switch that's used to establish either a continuous, electrical signal or a break in the electrical signal. And that's what your processor is made of, right? Either it receives signal or there's a break, like the faucet. We stop the water from flowing, or we close it, or we open it so it would flow, right? So here it talks about normal open, so it's either push or pull. So and the common that you would see with the basic logic gate, you would have the AND, right? In C++, it uses the ampersand. The OR, it uses the pipe, the double pipe. And then the NOT in C++, it uses the exclamation point. Okay. And so, or in most languages, you can type out A and D, right? I know in Python, you simply just use the actual, right, the text for it. So it should be able to understand it. Okay, so with the AND, how it's going to be is going to be like this. So it says that the AND gate, it takes 2 input, and all of, all the AND and the OR takes 2 inputs. You're going to have the X and the Y. Okay. The NOT is going to be a unary input. It's only going to take 1 single input. So that's the only logic that's going to take 1 input. The other 2 take 2 inputs. So the AND takes 2 inputs. And so when it would receive on, right, or off. So when it's on, it's going to push. And so the diagram of that is going to be like this. So you're going to have 2 input, and then it's going to have 1 output. So as the 2 input switches, the connection is then become established, as you would see in the diagram. So A and B represents the input, right? And then, so if we have both ones, it's going to push, and then it's going to output, okay, which is 1. And we'll look at the rules. Okay, so when we say when it's on or off, what do we really mean as far as electrical signal? So when it's push, it's going to receive a high voltage, which is at close to 5 volts. Okay, depending on the architecture, but in general, that's really a generalized statement. So you're typically, it's going to be about 5 positive volts. Okay, now so that means that it's going to cause it to close, and it's going to supply a high voltage, and that's what we see as a digital 1. Okay, so when we say 1, right, that's really mean on, and on means it's push or it's closed, it's received 5 volts. When it drops the voltage, when we get a 0, when it's off, the voltage is going to decline close to 0 volts. It's going to be very close. Sometimes not quite 0 volt, but it's going to be like very close to that. Okay. And that means that it's going to be open, and there will be no voltage, just like how we would have no water flowing. Okay. So when you see the 1s and the 0, all that means is you are going to receive 1 for high voltage, which is 5 volts, and then 0 for low voltage, right? So, and as you would see when we write out, like last week, when we have a byte, we have 1 0 0 1 and so on, right? So if you think about how that would be in the electrical perspective, right, it would just be volts, no volts, volts, no volts, and so on. So that brings us to what we would see as a diagram. Okay. Sometimes you would see it drawn like what you've seen on the website, but often you would see that this is how it's drawn. Okay. And there are a lot of different simulators that people use to represent, multiplexer and logic and gates in the system, in system design. Okay, so here you would have A and B are your input, and you would have the shape like this, like a D shape. And the way that I remember it is for the AND gate, the AND has the D, and it's going to have the D shape. Okay, so when you apply that logic, we would say A and B is going to have an output. So if A is 1 and B is 1, the output is going to be 1. So when we say 1 and 1 is going to give you a 1. Okay. So the AND gate has 2 input and it's going to yield 1 output. And the way it's drawn is like a D shape, D as in David, right? A D shape like this. So for our truth table, so when you have 0 and 0, when you have 0 volt with 0 volt, of course you have 0 volt. So 0 and 0 is going to give you an output of 0. 0 and 1 is going to give you a 0. So when we compare this to a truth table, right? False and false is going to give you false, right? False and true is going to give you a false. So when you write an if statement, you say if, right? False and true, right? That's going to be false. That's not going to execute. So when you, anytime with the AND logic, anytime that you have a 0 in the mix, it's going to output 0. And that's how I remember it. And it helps me. So, and anytime you have a 0, it's a 0. So 0 and 1 is a 0, 1 and 0 is a 0. 1 and 1 is going to give us a 1. Okay, so if I have an input, I have 5 volts and a 5 volts, I would get a 5 volt. And don't think of it like a plus or an addition. No, right? It's just logic. Okay, question. Okay, next is going to be the OR gate.
Professor, I have a quick question.
Sure.
Going back, you mentioned if for the AND, like the gates, if they were physically pushed, like the water example. So like for a keyboard, for example, if we physically push a button, does that change it from 0 to 1?
So, okay, so input is going to be a little bit different. So when you enter text, right, human text, your text is actually convert to a numerical value. If you're familiar with ASCII table, so if I type an A is equivalent to 65 decimal. So your system convert everything to number, right? What we know as number is also represent another number. And so that might sound really confusing, but so your question is, if I press the letter A on my keyboard, is it going to push something in? If it would be if you're using input with the logic.
Oh, okay.
So for example, if I have A, the letter A, which is 65, which converts to binary, and the letter B, right? It needs to, so in that case, it's going to take the 65, convert it to binary, and then the B, which is 66, convert it to binary. Then it's going to have the 0 and the 1s, and then it's going to operate the AND. So what that means is going to line up, which is what we're going to do, the 1s and the 0, because it needs to give you only one output, not two outputs.
Got it.
Yeah. And then after that, what it's going to do is if you tell it to display on screen what that output would be, it's going to take that value, convert it back based on the encoding format, right? Like what that would be in text, and then it presents it to you.
Okay.
Okay.
I got it. Got it.
Yeah. So I think a lot of the times when we think about text, we don't really think about the low level, right? But now as you understand this, everything gets converted to a number, a binary,
Right.
and then it's going to use that binary to process or compute, right? It needs to compute something, calculate, and then it's going to encode. So it goes through the encoding process and then give you back what you've seen. Now, we don't only use one encoding system, we use many, right? UTF-8 is one, and so on. And so what that is depends. So just a little sidetrack, right? This happens quite a bit. for my student in programming, I would give them a Microsoft Word document that has the code, and they would, when they copy and paste the code over to their application, the symbol doesn't translate, right? Like
Right.
quotation marks. Why is that? Because it uses different encoding system. One application to the next application, you know, the way that it's designed, it uses different encoding, and therefore you would have misinterpretation of symbol. It doesn't know what that is. It can't translate what that value is from one application to the other application.
Wow, that makes a lot more sense.
Yep. So now whenever you copy and paste code, right, and it's throwing an error and you're like, wait a minute, I have the comma, I have the semicolon, why is it doing that? Just retype it because it doesn't interpret.
Cool. Thank you.
You're welcome. All right. OR gates. So OR gate is when you would see that in the example here, they're using on, which is 1, right? And you know that 1 is when it's pushed or it's closed, so it flows, right? And so if you have any time that if you have a 1, whenever it's pushed, it's going to give you a 1. Okay, you notice 0 and 0, of course, you're gonna 0 or 0 is gonna give you 0. 0 or 1 is gonna give you 1. 1 or 0 is gonna give you 1. 1 or 1 is gonna give you 1. So that means that anytime one of the input is a 1 or true, it's gonna give you true 1, right? So the way that we draw the OR gates is like an arrow. Okay, we have 2 input, A and B here. That's just a representation of it. And then it's gonna apply the operator, and then it's gonna output 1 output. So if I have 1 or 0, I get a 1. So if I have 5 volts or 0 volts, it's gonna get a 1. So you see this in the if statement, right? You would say if condition 1 or condition 2, right? In that case, anytime that one of the condition is true, it's going to execute the body. Okay. In the and statement, if I say if condition 1 and condition 2 is this, execute the following. In the and statement, both of them have to be true in order for it to execute the body. So you see this a lot from the programming side. You've learned originally, you say, oh, that's how it is. But now you would see that, you know, from the low level, the processor, this is what it sees. Okay. So in the OR statement, anytime that you have a true, right, if you're using an if, it's going to execute the body because it's going to outcome true. Okay. So true or false is going to give you true. 1 or 0 is going to give you a 1. So anytime you have a 1 in the mix, there it's going to output 1 or true. Okay. Question. Okay. No question. Next is going to be your NOT. Like I said before, the NOT is a unary logic. That means that it doesn't require 2 input. It only requires 1 input. That's the exception, right? And we see this with the ones complement when we did that last week. So unlike the and the or, the NOT gate requires 1 input, and the output of it is simply the opposite. So if I start with a 0 and I NOT it, it's going to output 1. If I have false to start, it's going to output true. If I have true to start, it's going to output false. If I start with a 1, it's going to output 0. So at the electrical level, right, anytime that it starts with the 5 volt, when you apply the NOT, it's going to drop the voltage to 0 or close to it. And the way that we write this or we draw this is it's going to be the triangle, and you're always going to see the little round bubble next to it. Okay. So when, and this is standard. So you would see that this is a NOT. So A, not A, right? as you see there. Okay. So I'm going to pause here and then I'm going to go to the NAND gate in a little bit. Let's switch gear and we are going to look at your assignment. So what I did was I rewrote I put down the truth table again for you there for the logic gates for the and the or. So I'm going to do this with you. Let's take away the answer for now. Okay. So what you have is the way that we indicate the symbol in discrete math or discrete structure is the upside down V represent the and. I know all of these symbols and the drawing, the diagram, it can be very confusing, but the upside down V is going to be and. Okay. So sometime you would see this and you would know that it's and. Just remember that it looks like an A, right? That means it's and. It's upside down V. That's the symbol. So when we do number 2, we would use the truth table. And you can start from the right or the left, doesn't matter. Technically, we should do on the right, but since Microsoft Word moves from left to right, I'm just going to use the left side. 1 and 1 is going to give me a 1. Okay. 0 and 1. So if I look here, anytime I have a 0 in the mix for the and, I get a 0. 1 and 0, I'm going to get a 0. 0 and 1, I'm going to get a 0 again. 1 and 0, I'm going to get a 0. Oops, let me space that to line it up so you can see. 1 and 1 is going to give you a 1. 0 and 0 is going to give you a 0. And 0 and 1 is going to give you a 0. Very easy. So for quiz and exam, you're expected to know this. Okay. You will be given a question close to this, and you will know how to find the output based on the given input and the operator. Okay, any question with that? So make sure we remember the rules, the and rules. Anytime you have a 0, it outputs a 0, right? The only one that output ones is going to be the 1 and 1. Okay, for the next one, let's do it together again. 1 and 0 is a 0, right? 1 and 1 is a 1. 1 and 0 next to that is a 0. 0 and 0 is a 0. 1 and 1 is a 1. 0 and 0 is a 0. 1 and 1 is a 1. And 1 and 1 is a 1. I think I spaced too far there. Okay. And of course, your calculator, if you put it on programmer mode, right? You can also check it. Okay, by clicking the bitwise. And I'm using Windows 10 calculator. But most computer calculator, if it has the programmer mode, you will be able to see that. And you just have to select the bitwise to see the buttons. So if I need to input the binary, I just select binary, right? And then type in my value and then click bitwise. I can choose and or not and so on. So that you can use to check your answer. So as we already covered the OR gate, question 4 asks us, how many inputs will yield on output in the OR gate? So in the OR logic gate, anytime you have a 1, you get a 1, right? Any of the combinations. So if we have input A as a 1, that's going to give you the output 1. If you have input B as a 1, or both, it's going to give you a 1. Excuse me. So what you have is if at least one of the input is on or 1, it's going to give you an on or a 1 as an output for OR gate. Any question? And we can also look at the below table for the rules. Maybe type that one. And the symbol that we use to indicate OR in discrete is going to be the V. So let's do number 5. Let me move this down to the next page so you can see all together. All right, let's clean this up a little bit. Let me do this with you, okay? All right. So let's start with number 5. 1 or 1, we know that that's going to be a 1, right? Like here, you see the output. 1 or, yes, question?
Oh, no, I'm sorry.
Okay. 1 or 1 is a 1, right? 0 or 0 is a 0. 0 or 0 is a 0. 1 or 1 is a 1. 0 or 0 is a 0. 0 or 0 is a 0. 1 or 1 is a 1. I chose this because I want to show you that if you have one input and another input that's exactly like it, you're going to have the same output. Meaning that if my input A is the same as B, my output is the same as my input. See, when you're using OR. Any question? Okay, so that gives you a little bit of practice for the OR gate. Then we can do the next one. Let's do this together. Okay, so OR, right? Anytime that you have a 1, it's going to give you a 1. So here, number 6, 1 or 0 is a 1 because we have a 1 in the mix. 0 or 1 is a 1. 0 or 0 is a 0. 0 or 1 is a 1. 1 or 1 is a 1. 1 or 1 is another 1. 1 or 0 is a 1. And 0 or 1 is a 1. Very easy, right? And if you're not sure, you can always refer to the truth table, either in the notes or on the page of your assignment. And then when you practice, it's going to get easier. So as we talked about NOT gate earlier, we said that it would just be flip of the bits or the opposite of it, right? So in programming, we would say, if the result is not this, right, then it would execute whatever. It would print or, calculate or whatever, right? So in that case, with the if statement, it's going to check for the true condition. So let's say if I say, if the result is not 23, right, I would print wrong answer. Okay, then in that case, if I have my result as 24 or 25 or 26 or -8, right, it would still print because it's not 23. Anything but 23, right? Then it's going to print. I got the wrong answer. So you would see that not operator being used in programming for different purposes. One of the example we just stated. So for number 7, it says describe the NOT gate input and output. The NOT gate only requires one input. And the output is the opposite of the input. And so depending on the programming language that you work with, right? I know that we mentioned C++, we use the exclamation point to represent not. You can also type not, right? I know that C-based language like Python, it just is not, NOT. So you just have to see how the syntax would be for the operator. So the symbol that we would use, right, in general discrete math, we would see that this is going to be the symbol. It's like a negative sign with the drop. It's like a wiggle negative sign. So when you see that, it's also represent not. So if it's not 0, then it's 1. If it's not 1, then it's a 0. And I'm going to do this one with you. Question. So for 8, we can refer to the above table, and then we can just simply find the output. As you see, there's only one input. So if it's not 1, then the answer for 8, you start with the 0. If it's not 0, then it's 1. If it's not 1, then it's a 0. If it's not 0, then it's 1. If it's not 1, then it's a 0. If it's not 1, then a 0 again. If it's not 1, then a 0 again. If it's 0, if it's not 0, then it's a 1. And if it's not 1, then it's a 0. Right? So we generally get the opposite of the input as an output. And then we can try for the second one, which is number 9. So we simply flip the bits for that one. Not 0 is 1, not 1 is a 0. Again, not 1 is a 0, not 0 is a 1, not 1 is a 0, not 0 is a 1, not 1 is a 0, and not 0 is a 1. There we go. Any question on NOT gate? Like I said, we are expected to know how to do this for quiz exam, right? And this will make a lot more sense when you start doing programming on Thursday. I know some of you already took CIS7, which you dove into programming with C++, right? So in computer science, as you take some of these classes, okay, what it is they're pieces that's going to be put together. So at the end, you're going to see the bigger picture, right? We are going to give you a little bit more in depth in each of the class as you take it. So be patient with it, right? Like it is a hard subject, and some of you might find that easy, but as you learn a lot of the concept, it's going to be like, you're going to be like, oh, that's why it's like this. Oh, this is why it's like this. So you're going to see the correlation with programming and the correlation with the calculation and so on. Okay. Okay. That would be for 8 and 9. Any question? And it's okay if you want to handwrite it out, right? If you wanted to type it, this assignment is designed so you could do either. Some students prefer hand type. I'll take that too. All right. Then next, we are going to talk. So I'm going to switch over to the notes now. We're going to talk about multiple gates. Okay, like 2, like not and. So NAND gate or a not and is the opposite of and. So simply you would have an and result and then you would apply the not with it and get another output. So that will be your final output is after you apply the second gate. Okay, so not and gate is the opposite of and gate. It is one on if and only if it is not the case that both of its input are 1. The NAND gate can be constructed from AND gate whose output is attached to a NOT gate. So what happens is you're still going to have 2 input, X and Y or A and B. It's going to operate the AND, get an output, then it's going to operate the NOT and get the final output. Okay, so there are 2 steps in that. And so here we're going to come back to the components. Okay, it says that it is the simplest logic gate to construct from a common electrical components, transistors, which is what we know that's the composite of our CPU, resistors. You might learn this in physics, or if I don't think any of you took my summer non-credit classes with Arduino. Resistors are used to regulate, right, the amount of voltage that you can receive or use at that particular component. So resistor, you can use it. So we would use resistors to either keep it at a certain volts, right? Because your current is always going to be like in a range. It's never going to be stable. So you can use it to make it very stabilized or control it to a certain volts and or wires and so on. So the fabrication of what you see with the integrated circuits, right? Every board that if you go and you buy a USB drive, it has integrated circuits. If you go and you buy a hard drive or so on, all of those components have some kind of IC. We call it IC or integrated circuits. Or any components you see there's a green board on it, right? Even like, some house alarm now, your smart devices, all kinds of things have integrated circuits, right? It has some kind of processor, it has some kind of things to really control. So knowing that NAND is going to be the preferred gate, right? It's the simplest to use for those type of components. And it is known as the logically complete for every conceivable truth table logic gate and circuit that can be constructed solely with the NAND gates. So we can draw this with the and then we add the little bubble that would make it and not. Okay, so it's gonna get the output from the and then it's gonna not it, and we're gonna have the final result. So if we say A NAND B, if we start with a 0, we're gonna get a 1, right? Because if we have A and 0 and 0, that's a 0. but we need to NOT it. So that's going to make it a 1 and so on. So 0 NAND 1 is going to give us a 1. 1 NAND 0 is going to give you a 1. 1 NAND 1 is going to give you a 0. Okay. So anytime that you have a 0 in the mix for the NAND, you're going to get a 1. Conclusive statement there. Question. So before we switch over to the exercise, I'm also going to go over the NOR gate and exclusive OR. Okay. So the NOR gate is the opposite of OR. It is on or 1 if and only if it is not the case for at least one of its input 1. The NOR gate is constructed with the OR gate whose input is attached to the NOT gate. So it's OR and then get the result and then it's going to NOT it. Just like what we talked about with the NAND. So when we simply draw this, we would have an OR gate attached to the NOT gate, which is the bubble. So when we look at the truth table, 0 NOR 0 is a 1 because when we OR it, it's a 0, right? And then we NOT it, it's going to make it a 1. 0 NOR 1 is a 0. 1 NOR 0 is a 0. 1 NOR 1 is a 0. So conclusively, we can say that anytime that we have a 1 in the input, we're going to get a 0 as the output. Anytime we have a true in the input, we're going to have a false as the output when we're using not or nor. We might finish a little early today. Just wanted to see. If I'm going too fast, if you need to explain something, let me know. Sometime at the end of the day, sometimes I talk fast. So let me know, okay? All right, question.
Professor, you just quickly, you mentioned a conclusive statement for the NAND, and I missed that.
So for NAND, right, we can say that anytime one of the input has a 0, it's going to output 1.
Oh, okay, that's what it is. So either A or B. Okay.
Yep. And then for the NOR, anytime that you have a 1 in the input, it's going to output 0. So in the assembly, sometime I would introduce them to multiplexer, right? What we call MUX. And if you get into like electrical engineering and things like that, you would need to work with those diagrams. But for computer science students, sometime that will be helpful to just be able to understand these gates, how they're drawn, right? The logic behind it. So you would see like there would be, so in the case when we're looking at like an application or the overall picture of things, right? You don't only see NAND, this and this, you would see a combination of these. You might have like, you know, multiple gates combined, and you also have in the case NAND not combined and so on. You know, and then logically it's going to produce something for you as what you have as an input. Okay. All right, question. So exclusive OR. XOR gate is what we call exclusive OR. So whenever you see XOR, we say exclusive OR. Okay. It is on or 1 if and only if one of the input is 1, but not both. So very similar to the NAND gate. The only exception is if they're both of the input are 1s, then it's not 1. Okay. So the logic gate representation of the truth table for the XOR is shown below. XOR is useful in implementation of binary arithmetic, like, so it's going to be equivalent to some addition. That's what it's telling you. So when you're adding two binary digits, so last week we spent a little bit of time on carry and borrow, right? When you are using when you're carrying into the left column, okay, your computer needs to operate that. Okay, so the way that it's designed, your processor is designed is when you're doing that, you're starting from the right, you're going left, and when you're carrying into the column to the left of it, it needs to represent that somehow. Okay, so I highlighted here, it says that note that the exclusive OR gate gives the proper output for at least significant for the least significant bit by adding the 2 bits, and further note that the AND gate gives the proper output for the most significant bit or carry by adding the 2 bits. So this is what we call a circuit that they design is called a half adder. A half adder is designed to store that carry bit, right? Remember how when we do like a 1 and a 1 is a 0 with a carry? Well, that carry bit needs to go somewhere. It doesn't just magically appear, right? A computer is very physical in how we would treat. So either you have some kind of electrical signal or there's no electrical signal. So we have to find ways to really represent that carry bit. So what they did was they created what's called a half adder. And this half adder is used to carry that bit from one column to the next, so that way it can be implemented into the addition, right, of all the subsequent value that we're adding. Okay, so now that that you would see. So on the bottom of this, it talks about the ripple carry adders. And it just kind of, I just summarize it in what I state, that when you add two binary number, one must in each column that would sum the corresponding bit for each of the input together, that any of the input carry producing an output bit that would be a carry bit. Okay, so it needs to carry that bit. And so for the exclusive OR, it would be the OR diagram with the line, strike line down for the input. Okay, so when you have A XOR B, it's going to get a when 0 XOR 0 is a 0, 0 XOR 1 is going to be 1, 1 exclusive OR 0 is going to be 1, 1 exclusive OR 1 is going to be a 0. Okay. So if you do the half adder circuit, like what we talked about for the carry, it's going to be an exclusive OR combined with the AND. Okay, so this is what, so the two logic gates combined together give you the half adder. So you can carry. So that way it can compute that carry to the next column. There's no magic, it's just math, right? Okay, question. And then if you want to go further, it also talks about that here. So a full adder, like, you know how when you carry and keep carrying and carrying from one column to the next? Sorry, my alarm goes off because normally I teach another class at 7 on Monday and Wednesday. So the full adder, you would have two exclusive OR, two AND, and an OR. And this is the diagram for a full adder. So it's a half adder with another half adder and an OR. Okay. So you guys are getting a little bit more than some last semester. I don't think I spent too much time on it. But because we're on track with the schedule. All right. So answer number 10. Compare AND gate to the NAND gate. The difference between these gates are the NAND gate output is the opposite of the AND gate, not after AND. One sentence summary. So that will help you remember, right? I'll leave it there for a little bit. We still have like an hour or so. No worries. Question. So on the following page or the below section, we would also see the truth table for not AND or NAND. And then we just need to manually compute it. Let's do this together. Okay, so start with the first one, 1 NAND 0. So you can just look here at the table for reference. That will be a 1, right? 1 and 0 is another 1. 1 and 1 is a 0. 1 NAND 1 is a 0 again. 0 NAND 0 is a 1. 1 NAND 0 is a 1. 0 NAND 1 is a 1. Remember, anytime there's a 0, we got an output 1. And then 1 NAND 1 is a 0. Easy peasy. There will not be a truth table for your quiz and test. Okay. Quiz, I don't mind if you can use your notes because, and it also gives you 3 attempts, but for exam, I do use lockdown browser, so no notes there. Okay, just quiz, you can do multiple attempts and you can use your note as reference if you like. I'm fine with that. For 12, same thing. We just need to compute, and I'm not going to do this one. So there will be a few exercises you have to do on your own. Okay. Practice. You use your truth table, go down each column, and then put down your output. Any question? So for 13, it asks you to describe the construction of the not OR gate or the NOR gate. So the not OR gate is the opposite of the OR gate. The not OR is not of the OR output or not after OR output. Okay. So we OR it first and then we apply the not. So we can do it in 2 steps if we don't remember the truth table, right? Like if you remember the OR rules, then you can just OR it and then flip the bits. Same thing with NAND. You can AND it and then flip the bits, where you don't have to remember all all these rules all at once. So all you have to do is remember the and, the or, and the not, and you're golden. Question. Okay, so below, right below 13 is your not or nor truth table. Then we just need to find the output for number 14 with the given inputs. So let's take this up. Let's do it again. Okay. 1 nor 0 is 0. 1 nor 0 is 0 again for number 14. 0 nor 1 is also a 0. 1 nor 0 is a 0. 1 nor 0 is another 0. 1 nor 0 is a 0. 1 nor 0 is another 0. And 1 nor 0 is a 0. And if you look at the input, right, the top line, right, when it's 1 down here, it's a 0. So of course, it's going to give you a 0. And then anytime you have the 0 in the mix, it's a 0. So everything is off there or false. Question. And then you can try number 15. Very easy. It's slightly different than 14 as an output, but so. And remember that these are not like addition or subtraction, right? They're different. So just gotta know how to use the logic. All of this is pretty clear, straightforward until you get to the end. Conjunction and disjunction and negation. This part, the way the book represented, and I think most discrete structure book represented, is always so challenging for students to digest this part. So save the hardest part for last. And I didn't require that you do any exclusive or. You can practice if you want, right? Exclusive or is used in cryptography. It's used in a lot of different things. Blockchain for crypto, currency. Yeah, there are a lot of applications in a lot of these logics for many, many things outside of just written programming statement. Question. Okay, so make sure that we have the answer for 12 and 15. That's the only ones that I didn't provide. I'm going to switch back to the notes. So 3 kind of sum up a little bit from chapter 2, right? Truth table, 5 volts, and 0 volts, true or false. Oh, Zoom just notified me that you can see my screen. I thought I was sharing all this time. Okay. Let's look at the operation again and look at the operators and Boolean algebra to correspond. So we already did that for bitwise. So we touched on 0, 1s and how we apply these operators and or not. Also, we need to really interpret this in CNF and DNF. So the AND operator represents conjunction. Okay. X and Y represent conjunction. The OR operator represent disjunction. The NOT operator, even though I feel like this is misleading, NOT operator represents negation. But you learned 2's complement last week. Negation doesn't complete until you add that bit in the front to store the negative sign, right? To represent the sign number. So at least at the 1's complement is the NOT. So you can think of it as negation, which is NOT is really the opposite bitwise. Question. Okay, so all of this is just truth table represented with the symbol and true or false. Okay. In our assignment, you can simply put down that CNF stands for conjunctive normal form. Let me type that out. Would help if I type it correctly. CNF. We would use the AND operator to connect the terms, meaning that let's say you have X plus Y and Z plus K, right? So the term is X plus Y, and we're going to AND it with Z plus K. And I'll show that in format shortly. So we would use the AND operator to connect the terms. And inside it, we would have the OR operator inside the terms, inside the parentheses. So the OR operator would then be used within the term. The disjunctive normal form, or known as DNF, this uses the OR operator to connect the terms and the AND operator to use within the term. So inside it's AND, outside it's OR. The other one, the conjunctive, outside is AND, inside is OR. And for negation or the NOT, operator is used for one or the other. It could appear there. Question. Okay. So I found that when I have these statements generalized and there, it helped my students kind of see how the form would be, because when you look at the example in the book, it can be challenging looking at like how it is inside the terms, between the terms, and negation. Okay, so keep in mind that conjunctive, you're going to have and connecting the terms and or inside it, inside each term. Disjunctive or connecting the terms and inside each term. That's the main difference when you're looking at that in general. Okay, so let's take a look at some example first. And if you wanted to see how the math theories are applied with the logic, right here, it gives you the list of, cumulative law, how that would be used to prove how the logic would be equal. And also proof there. Are you going to be required to do proof for this chapter? No, there will be a chapter that we would spend on proof, but not as extensive as your calculus class or other classes. So here what we see is we have the definition again, the conjunction clause, which is the upside down V, and then the disjunction is the or, which is the V. So the example that you would see, and I typed this out without using the symbols, I hope that that interprets well, easier for you to read it. So when you have this A or B and C or D like this, the inside of the term is or, and from one term to another in between the terms, we have an and, that's considered conjunctive. Okay. In some case, you also see negation within the term, or it would start with negation. So you would have A or B, right? And then on the outside, it's and, not C or B. So in this case, it's also a conjunctive normal form. And in C++ statement, we might have something like this, right? Int h and int time, or not in pressure, like that. So in that case, it is what? Conjunctive normal form. So here, this is the author's example, right, for the formula and the clauses. But if you take away some of the understanding from this part, in general, that will be all right with me. And that means that you can apply. So here we have A and not B and, right? B or C, that's conjunctive, right? Because the or is inside, the and is on the outside in between the terms. Okay, and then again, we have A or B or not C and not B or A or D and so on. So when you look at this, you know that it is conjunctive normal form because it uses and between the clauses or the terms and then the or inside each of the term. Or it can simply be this, A and B. Okay. And this confused people because this should be a parentheses outside right here. I would write it like that. So A or B inside the term. So CNF. Okay. and it gets crazier. um, so here is, you know, another set of example, right? We might have negation on the outside where it knots everything, it negates everything, or we would have it on the inside. So in this one, it says that this is a disjunction, right? For the one clause, A and B is a conjunction. So inside the term, it is a conjunction, right? Like what we said. For the disjunction, inside is conjunction and then outside is disjunction. So when it's or on the outside, you know that it is a DNF disjunction. Okay, so you would go with the operator that connects the terms or on the outside. That will be the safest generalized conclusive statement. All right, let's try the exercise now. Any question? Okay, so 17. It's going to ask you to determine negate X, right? Or Y or Z and X or Y or negate Z. Is it a CNF, conjunction normal form, or DNF, disjunction normal form? So you ask yourself first, which one is used to connect the term? Is it conjunction or disjunction? It's and, right? So it has to be a conjunction. Okay, so if we write it out without the symbol, it will be like negate, you know, negate X or Y or Z and X or Y or negate Z. So this is a CNF. And I just want to reiterate this, right? Conjunction normal form, you can say conjunctive, it's the same. That will be or operator used within the term and operator used to connect the terms. So for 17, that is a CNF. And the reason why is or is inside the term and then and is to connect the terms. And this came from your notes. Okay. You can also reference your note. So for 18, this is a mix of things where it doesn't fall into one or the other. Okay, when we look at this, we would say it's actually this. It is not, right, P, and then it has an N on the outside, and then it's not Q or R, and then it does an or P or not Q. Wrong symbol. So this is neither. Why? Because first it's using the and to connect the first two terms together, even though there's a negate there. Then you have an or operator used to connect the last two terms. So it doesn't fall into one category. Okay, it's both. Or it doesn't, it's not quite CNF nor DNF. Understand? Any question? So we will be required to distinguish these. You will be given questions on quiz and exam that will ask which form it is, and you will have to know. Okay. Based on the given terms.
Professor, how do you make the not symbol?
I cheated. I actually there is a symbol. Let me see if you can just use the negative sign.
Oh, okay.
Yeah, use the negative sign, but there is a symbol. I think it's in the font. Let me see if I can find it. Okay, 1 second. You do insert symbol, and then you have to spend time like looking in the symbol.
Okay.
Yeah. I copy and paste it from the either one of the texts, but yeah, you can use the negative sign, it's fine. And you notice that how they write it, it's actually the other way. Yeah, I was only able to find it going this way, so. But you get the idea, it's just a negation. All right. Last one, okay? We talked about the other one is kind of doesn't fall into either category. It's kind of like a combination of the two. So on this one, also a tricky one, right? So you have P and Q and R. So at the start, it's good. It's good for that term. So it could be disjunctive. And then you have the or, so that kind of make it almost disjunctive. And then you have a negate P, and then you have the and thrown in there, and negate Q and negate R. So the last part, make it not D. So the last part is change it from DNF to something else. So it is not DNF or CNF because the first half is DNF. And then when it got here, it will be a negation. And then the last half, it would make it CNF. So it's a combination as well. So the answer for that will be if it's not DNF or CNF, the AND operator is used within the term, the OR operator is used to connect the term. The OR operator is also used to connect the negated term. So it's somewhat disjunctive and conjunctive at the same time. So will you get something like this on the test, right? In that case, you will have the appropriate choices to select. Questions. And then I just included, the same stuff from the notes. So if you have the notes document, you can always reference that. And the assignment is really designed for you to go through the notes with me, because I know you have like tons of other classes that you have to do homework reading and assignments for. So this is really designed to make you or encourage you to follow along and do it with me, and so you can understand and ask questions. Okay. All right. Any question? Okay, so if you finish with the assignment, you can upload it into the Unit 2 assignment, and then I will process the grade down the line, maybe a few days from now, but it's not due until Sunday. So you do have some time that you can spend on it, so no rush. But I did post the lab for this week. So if you do have time, some of my students, they told me that for my class for the lab, what they did was they rewrote all the code, right? They type everything out. And so, but I do give you time to input that, and I will explain the code line by line. So they found that it would be more useful. So if you do have time this week before Thursday, you can check out the assignment. Let's go to it. Here it is. Okay. And I use everything module because sometimes if you click in the assignments, sorry about the confusion last week, I fixed the problem. So you will have one that's going to require you to check the binary. Okay, so this is when we would apply programming with what we've learned previously in the last couple of this week and last week. So we are going to do a logical operator program. We're also going to do, you know, the and, the or, the not, which see here it's indicated as a till, which is a binary ones complement. Okay. So we're going to do a program on this, and then I screenshot it for you already. So all you have to do is to write it out. And then instead of using the given values in the example program, you are going to use a different value, 40 and 17. Okay. And then I'll ease you into some of the more complex program as we go. So then we are going to use bool type, and I'll explain the bool type. Giovanni asks, a more complicated way to type the symbol is to represent Alt numpad 169. I'm using window though. It is an Alt code. Okay, good. Thank you for sharing that. So you can write that symbol. All right. So the second exercise for the lab, we are going to use the bool type. And then it's super easy. So I want you to show you or jog your memory of how you can use bool type, and also you can also use keyword like true or false, not true or not false with the symbol in C++. And then you will have an output. And then we are going to use bool alpha. And bool alpha is going to take the bool value and make it into an alphabet, which is text, so we can see whether it's true or false. So we're going to do that. And then we're going to do some more programming, like a regular program where we would use the operator to apply to the condition, right? Like income and you know, like for loan applications and so on. You see a lot of those. And then we're going to use the logical and, which is the double ampersand. Okay. And that will be it. So in general, your lab exercise would be about 5 or even fewer, right? Because I know it would take time for you to enter your code, run it. And you can use Visual Studio or online compiler, that's fine. If you sign into the online compiler, I suggest that you store your program somewhere in the case where, let's say that you submit and something drastically happens where I don't receive your assignment somehow, you know, you don't want to redo all of them. So you just simply go back to the program and be able to screenshot it for me. I do a lot of screenshot stuff for all my classes. It's the easiest way that I can see that you've done it. And so I'm sure that you've done that for other classes as well, but you can do Alt print screen on your keyboard for Windows, and then on the Mac, there are specific ones, but Apple has a whole help page on it. So you can also screenshot it. You can also use Windows snippet tool, right? You can do it this way, where you can snip portion of it instead of the active window. When you do Alt print screen is when you can take the active window and then paste it. Okay. Submission for all assignment, I prefer that it is in .doc or .pdf. So if you use Mac OS, you know, convert it to PDF for me. I use Windows 10 in general, right? Like we have an Apple system at home, but mainly I don't use it. So then, you know, that way I have your assignment. Otherwise I can't grade it. So if you if you have Apple system, don't send in the dot pages. If you do, convert it for me and resubmit, okay? And you won't be penalized if that's the case for late work. So that kind of give you the preview for lab 2. And in general, you know, I'll explain it, we'll do it together, and by the end, you should be able to finish and upload. If not, you can spend time on it and complete it. Make sure you turn it in before Sunday. And I don't think the holiday impacts y'all, but I think the Monday and Wednesday class will be impacted. So if you have class Monday and Wednesday, right, keep in mind that we have a holiday coming up. So Monday, the school is not operating, even the online one. Okay, question. No question? Okay, type your name into the chat. I'll stick around for a little bit. I'm gonna stop recording though, because it would